can you try sharing your screen?
Yes, I'm just doing it, and I hope it also works.
Let
I
me
think
see.
you should see it now
Y-
if
y-
possible, and I can also
Yes,
start
yes, yes, yes. Yeah. So,
the
okay. So
video.
Daniel is a faculty at University of Duisburg, Essen, and he works on different topic related to quantum chaos, complex system, and so on and so forth. And today he's going to talk about kicked spin chain from periodic orbits to localization. So, okay, Daniel, stage is yours. And okay, thanks.
Thank you very much for the kind introduction, and I also want first to thank the organizers for putting together this nice workshop and also for giving me the opportunity to give a talk here. I will just directly start with the outline of my talk. That didn't work. I have to see how I get to the next page here. Now we are at the next page, I think. Now it's okay. So we are already unfortunately approaching by the end of this workshop. So I think it's good to just give you at the beginning a bit a connection also to the topic of the other talks and to say what we are doing differently and how it's connected. So I'll also consider a system which is, however, not self-dual, but where the dual operator is involved, so to say, the spin chain you have also heard about in several talks, the Ising spin chain. The last talk I think we heard about it was from Boris, where he also gave some results on it, but I will talk on different ones. Then in the second step, I will give a first application of this duality, namely the quantum classical correspondence in many body systems, so spin quantum number greater or equal to 1/2. So you have heard already some approaches about this Feynman path integral approaches. However, they were always not really connected to they were always connected to averaged quantities, so to say, by pairing of periodic orbits. This is, however, not the case here. We are really willing to extract the periodic orbits from the trace formula for a quantum many-body system in a spin chain with s greater than 1/2, also by using the dual operator approach. And finally, I will return to a spin 1/2 system, also the kicked spin chain. And here I want to show you the transition from the ergodic to localized behavior. This is closely connected to that what John Chalker explained us this morning. However, I want to start here from a specific example and extract and get the properties by looking at this specific system. Good. Let me first come. You have seen that already, I think, now several times in different topics. To the system, we are looking at the kicked spin chain consisting of an interaction part on the one hand and an external magnetic field that is pulsed and indicated by this delta function here and periodic boundary conditions, making essentially this chain shown here to a ring. So we have here the nearest neighbor Ising interaction, then the spin operators corresponding to spin quantum number S, and here then the external field, which consists of X and Z direction. As we have already learned, this is the system which is relevant in the sense that it is relatively simple still, but it is not anymore exactly solvable and only exactly solvable in the disorder-free case for spin equal 1/2 and for certain magnetic field. So Bx equals 0 is trivial and Bz is solvable by the Jordan-Wigner transformation. So to say, it's a simple non-integrable Floquet quantum system and shows an interplay of interactions and disorder. The time evolution, and now I want to explain you here our approach, how we actually got to the duality in this context, is given by the product of the two time evolution operators concerning the two Hamiltonians. And our problem, which was also the main motivation to then introduce this duality, was that the time evolution operator has just a too large dimension if we look at a real many particle system, so with many components. And so to say, numerical studies are not anymore possible, and that's why we then introduced this or used this duality in time and particle directions, indicating that we don't evolve anymore our spin chain, here given as a certain row in this picture, from one time step to the next, which is indicated by the operator u, but we look, so to say, at a certain part, so a certain particle of the chain, and just evolve it by the operator u tilde, so to say, to the next particle in the chain. This is, however, possible in this case because we can treat particle number and also time on equal footings, as they are both discrete variables, so to say, their role can be interchanged. And this allowed us then to introduce the non-unitary, in general, non-unitary dual operator with respecting this trace relation here. And naturally, as we introduced here time and particle number, we also interchange, they also interchange if we look at the dimension and compare the two dimensions. So implying that this dual operator is especially suited if we are interested in short time dynamics, where this dimension is especially small. So let me now come to the first application. So to say, there I want to briefly go into the field of quantum chaos. So as most of you will know, quantum chaos, so to say, studies the connection between classical mechanics on the one hand and quantum mechanics on the other. In classical mechanics, there are two so extreme kinds of motion, the integrable one and the chaotic one, here indicated on the left-hand side for the rectangular billiard and on the right-hand side for the chaotic Sinai billiard. And now if you want to move into the quantum mechanics from the classical mechanics, you are now in the good situation in the integrable case that you have conserved quantities. So to say, if you have d degrees of freedom, you also have d conserved quantities, so you can directly quantize your system by just taking the action variables and claiming that they are integer multiples of h bar. This is, however, not anymore so trivial in a chaotic system. There we can, however, get a connection due to Gutzwiller relating the density of states to a semi-classical expression. I will now explain it in more detail on the next slide. So to say, we have here the quantum level density, the train of delta functions, which is then related to some mean density and also to oscillatory part that is given as the sum of the periodic orbits to the energy E in the system with the containing the classical actions of the orbit and classical stability coefficients A gamma. This formula is on the one hand very nice and a very huge progress. However, it has always drawback that it cannot be tackled. You cannot tackle this formula very easily because you have here an infinite number of periodic orbits. So you can always think of infinitely long periodic orbits. So this sum is not really easy to perform. So one had to invent here a lot of tricks for resummating it. However, it is possible if you want to check this formula by simply doing a Fourier transform so calculating the Fourier transform of this delta function on the one hand, which can be just obtained from the spectrum, and on the other hand, the Fourier transform of this term here is just giving you, so to say, the action spectrum or the length spectrum. For single particle systems, this has been performed long ago. Here two examples, one for billiards, where this is just more or less a Fourier transform, usually with respect to k, then giving you the length spectrum. And for the kick top, an example which is very similar to ours, you can also do that. So you see here the examples for billiards, for example, the symmetrized Sinai billiard. You see that exactly such a Fourier transform just gives you just peaks at the positions of the periodic orbits. So our aim in this first application that I present here is now to generalize this to many body systems, so to say, to identify the classical periodic orbits in a non-integrable many body system and their impact on the quantum spectrum. We, of course, expect here, compared to the single particle system I had on the last slide, richer phenomena due to the fact that we have relative motion in the many particle system. So here two extreme kinds again. On the one hand, fully incoherent motion, where all individual particles just have random momenta. And on the other side, fully coherent motion, where all the green balls shown here move collectively with respect to the yellow balls. This should be an indication of so-called giant dipole resonance in nuclear physics, where it is observed also that the cloud of protons, which would be indicated here by the yellow balls, is moving with respect to the cloud of neutrons, here indicated by the green balls. And we want to understand in this context the interplay of incoherent and collective motion for short times, and start with our easily accessible spin chain system. So here I have it again. Now the spin chain system, of course, consists of spin s particles, where s is usually larger than 1/2. In order to get such a semi-classical connection, so a connection to the classical dynamics in the system, we first need, in order to get such a classical connection, of course, the corresponding classical dynamics in this system. This is obtained by, so to say, unit Bloch vectors, which are just rotating on the Bloch sphere. And of course, if we have an capital N particle system, we have, of course, also capital N vectors and M. And the rotation is just mediated for t time steps by the t-fold application of a rotation around the z direction, which is just indicating this interaction here, with the angle also depending on the neighboring set positions of this corresponding n vector, and a rotation around the magnetic field axis. So illustrated also here by these corresponding cones. Then the periodic orbits are, of course, just given if we look, for example, for 7 spins just by 7 Bloch spheres, and for 1 time steps just by arcs that are yielding the rotations around, well, so 1 rotation around the magnetic field B, shown here, and 1 around the z-axis, indicating this rotation around the rotation that comes from the interaction between neighboring spins. So then, of course, to connect this classical dynamics and the quantum dynamics, we also need a corresponding trace formula, which we derived, and thereby we could relate the trace of the time evolution operator again to a sum over periodic orbits in the system, now of duration capital T, with stability prefactors I gamma and action S gamma. This is asymptotically valid, so that's why I wrote similarity sign here in the limit of large spin quantum number. And now one can, of course, naturally perform the Fourier transform of the action spectrum. And this naturally leads us then, not of the action spectrum, but of the trace of the time evolution operator, and this naturally leads us then to the action spectrum of the system. However, well, this would have been performed, of course, much earlier, such a calculation for a specific many-particle system if somebody would have come previously to the idea to just use duality. And this was also the main obstacle why it couldn't be performed earlier. So to say, this trace of, not a trace, but the evolution operator is of course very high dimensional. So to say, if we now look at an S-cut, which we have to introduce here due to numerical reasons, and this determines also the resolution of our action spectrum that we obtain. If we introduce an S-cut of only 10 and 20 particles, we are already at Hilbert space sizes, which are already astronomically large. So this is not a possible application. What, however, can be done is to replace this trace of the time evolution operator by trace of the dual operator. And naturally, S for short times, the dimension is very small here of this utility. It is possible to perform then this Fourier transform and to calculate action spectra. This is also what we did then. And so to say, I'm showing you here the results for t equal 2. We also have naturally results for t equal 1. However, they look very similar to the plot here on the left-hand side. So they're it's not possible to get so much information from them. And here we have distinct features for n equals 3 and n equals 4. I'm showing you here. So for n equals 3, we just have the situation that we have more or less a lot of peaks which are of the same size. I should also say what we actually see here precisely. So the black line we see here is just originating from this Fourier transform. So to say, it is just this row of S calculated numerically, and then we have here distinct peaks, and we can then ascertain each of these peaks to specific periodic orbits that we can just obtain by solving the classical equation of motion for the periodic orbits. And so to say, for n equals 3, we have, as I just mentioned already, a lot of peaks which are of equal height, indicating that there are several periodic orbits that are of equal importance. However, this changes for n equals 4, where we just have periodic orbits where we have essentially one peak that is dominating everything. And I will just show you now, if we come to an end of this part of the talk, that this is related to collective motion. This is, of course, especially easy in that case because we know that we have this quantum classical connection, so we can just identify periodic orbit which is related to degree 9, and by this we will then see how this periodic orbit looks like. But before, I just want to mention that this specific structure that we saw here on the right-hand side just carries over also to larger particle numbers, so to say, to particle numbers which are always integer multiples of 4. In that case, you can always find a similar situation, and you always find one large peak which is dominating the spectrum. And now, how can we explain this effect essentially? So this is due to the fact that we have, in this case, of four particles and also integer multiples of 4, we have the possibility that there's, due to the classical equations of motion, if you solve them, the occurrence of a large set of periodic orbits, so to say a 4-dimensional manifold of non-isolated periodic orbits, so to say, which all have the equal action. And this has also the special feature that in this case, so to say, we have a realization of collective motion in the sense that the individual spins that are here indicated, so by the 4 arrows, just are tied to this solid body in the middle, and they just rotate. So this solid body in the middle just rotates as a whole, and there's no computation relative of the particles with respect to each other. So this now brings me to the first summary of this part. So we have computed, I've shown you how to compute the classical orbits from the quantum spectrum for such a many particle system by using the duality and allowing only by this to do such a computation. And we have found that this is a unified description to get, on the one hand, collective and also incoherent single particle dynamics as it's naturally expected for a many particle system. So let me now come to the second part, the spin 1/2 case, and look here for ergodic or localized behavior and the spectral statistics of such a system. So as you have heard already in many previous talks, the dual operator is in general a non-unitary operator, but for very specific parameter values, it becomes essentially unitary. And we now want again to look at spectral statistics of this system. We have heard some similar introduction also in Bruno's talk yesterday. And what we now want to look at is, so to say, the distribution of these eigenphases of the operator U tilde around this self-dual regime. We know that there is the Bohigas-Giannoni-Schmidt conjecture, which just states that the spectral properties of the system with classically chaotic counterpart are determined by universal random matrix theory. Of course, the nice thing is here that you know that there is a classically chaotic counterpart, which, however, is not the case in the spin 1/2 system, and which makes it especially interesting, and which I want to discuss now in the next part. So we will not look as just shown here at the nearest neighbor spacing distribution, here shown for the Wigner distribution, which is characteristic for the chaotic Sinai billiard, or the Poisson distribution, here shown for the rectangular billiard, but I will now look also at the spectral form factor, which is just given by the trace of the time evolution operator squared and then averaged, or also by duality, just by the dual operator. It can be imagined as the Fourier transform of the spectral autocorrelation function. And as I just said, this is of course interesting. As in the spin 1/2 case, there's not a classical counterpart, or that's what at least the motivation why we wanted to study it. And so to say, we now wanted to find out what is the behavior of this system, where two hypotheses could be true. So to say, it has chaotic, sufficiently complex dynamics, which would lead to a behavior in accordance with random matrix theory, and on the other hand, disorder and interaction, which would lead to many-body localization. So there have been, of course, previous results on this system already. So to say, in the self-dual case, the system is well studied. It's known that it behaves according to random matrix theory. However, what is not so well known, and what was also the motivation for our study, was what happens to this specific system in the non-self-dual case. There are also different related results like that for large times, so not times which are just a few multiples of the kick time, but times which are of the order of the tallest time, for example, we find random matrix series found, and also if there's an average over parameters, many-body localization is obtained. So we now want to characterize the system behavior and the spectral form factor in this regime, marked by the question mark, and show how this transition happens and study that in great detail for this specific system, if this is a transition from ergodic to localized behavior, or what happens there. So we are looking, just to be precise, at this spin chain given here, where there is this order in the Z component of the magnetic fields, which we are also averaging over then. And we now computed the spectral form factor for this specific system, which shows for delta J equals 0, a plateau, and then a sharp increase, which might remind of some transition for larger values of delta J. And that we now wanted to study in detail. So first, we wanted to understand what kind of transition is happening here. Therefore, we chose a slightly different way of plotting the data now with versus n of the logarithm of the spectral form factor for various values of delta J. And we found that essentially this result just consists of two horizontal lines, one just horizontal, no, sorry, not horizontal, but one horizontal line and then a line with a finite slope for larger n values, and for small n values, a horizontal line. So what does that mean? We can indeed indicate this behavior starting from the spectral form factor to something like localization by just assuming that our spectrum falls into independent subspectra. So to say, the form factor is then given by the RMT form factor as long as the particle number is smaller than this particle number that is needed, that is contained in the subsystem. And as long as this number of subsystems is larger than 1, so mu is larger than 1, we obtain for the spectral form factor the RMT form factor to the power mu, which then indicates different behaviors, so to say, behavior which leads to a horizontal line for n smaller than nc, and a line with a certain slope for n larger than nc. This is exactly what we observed here, which might indicate then a transition to localization. Now let me come to some analytics. We now wanted to describe this form factor also by perturbation theory, or that was our starting point, in the vicinity of the self-dual regime. So to say, what we used in this context was that we could block diagonalize our operator U tilde by just seeing that it's invariant under cyclic permutations and reflections, meaning it then falls into T+1 block. It was shown by the Posen group that one eigenvalue per block is equal to 1. And we now saw that if we go away from self-duality, then this eigenvalue that transforms into this unit eigenvalue is essentially the dominant one. So if we now do this perturbation theory in this regime of small delta J, we were then able to analytically compute the form factor, so to say, by computing this bk as a function of time, and by this also getting then in the limit of large particle numbers and small delta J, then an analytic expression for the spectral form factor. That we could now compare with the numerics, and we found that especially for large n, we have good agreement in this case of relatively small delta J. And essentially, if we go to large chains, we also found that in this regime of relatively small times, we also can get a further simplification by just noting that there is only one dominant lambda 0 plus, which then allows to reduce the parameter space and to just get the spectral form factor just from this largest eigenvalue of the dual operator, as we also heard this morning. You see it here in this plot, where only this largest eigenvalue is getting larger than 1 for delta J non-zero, and the other ones get slower or even imaginary, as indicated here by the red lines. So from this, we can also then get analytical expressions from this perturbation theory, so to say, for the size of the localized subsystem and also for the Thouless time. So we have this expression for the form factor, which is just the mu's power of the RMT form factor, and also our result independence of this single eigenvalue. And from that, we can just compute NC. However, it is not really localization as we see immediately, as the corresponding NC is increasing with time, meaning essentially if we go to large times, we will just find a delocalized system in the sense, and additionally, of course, also the perturbation theory is no longer valid in that case. And the same is also indicated by looking at the tau-less time, where we just see that it also diverges logarithmically with n. So that means no true localization in this perturbative regime can be found. And we now just went to the other extreme of j equals 0, so the non-interacting system, where the system is essentially integrable and we could compute analytically our spectral form factor, or in other words, this largest eigenvalue, which is the only non-zero one for this system given here, and also perturbatively then around for small values of j. And we, of course, know that in this case, the system as it's integrable is trivially localized, so there must be a transition in between or at some point, some of the points. This is also supported by the fact that we could now also diagonalize the, or we could obtain this largest eigenvalue just directly from the operator u tilde, and we see that if we average over these oscillations of period 4 indicated here, we just find that there is a crossing of lines, so to say, for this largest eigenvalue. And as this largest eigenvalue is, of course, related to the localization lengths or the size of the localized blocks, one can assume that there is a transition to localization. The same is also indicated by the R value. Here, I think we have heard this already several times, so I will not explain it in detail. Here shown from 7 to 11 particles, which is also an indication for many-body localization. However, both results up to now were just for very relatively small times possible, or for relatively small n. So we were not fully satisfied with that and tried now to invent a quantity or to use a quantity which was then also allowing us to go to larger times. And that we just looked, this we just obtained by looking, so to say, at the relation in the localized regime that the form factor is just given by this lambda 0 plus to the power n. And inverting this relation, we can just obtain this lambda 0 n, which we by, or lambda 0 plus, as you wish, just by this ratio of form factors for adjacent particle numbers. And naturally, we now will find two regimes. As long as this expression given here is true, we just know that there is no dependence on the particle number, and so to say, all the numbers are the same. And then we know that we are in localized regime. However, if this is not true, this relation, which turns out to be the case if we go to larger times, then we just obtain, so to say, a lambda 0 n RMT, which is indeed depending on n, and which shows that we are not in the many-body localized, but in the RMT regime. The advantage of this analysis is that this form factor can be computed for much larger times compared to this eigenvalue lambda 0, where we had to stop at 20. And here we can now go up to times which are of the order of 2000, which is naturally much, much larger. And that we did here. So we computed this lambda 0 n, just as I described you, from the ratio of spectral form factors. And here in this plot, it's shown now, if you look at ABC, that just indicates that we chose different values of delta J. Here the first two below the localization transition and the second and the third one above it. And we also chose different numbers of particles, which are just indicated here as different colors. And we see essentially this behavior as we would have also expected it, namely that for short times in A and B, we find something like localization. However, this localization remains true for really short times. And if we go to larger times, then you see here, for example, for the plot A, this quantity lambda 0n then turns into this RMT quantity, so to say, no many-body localization anymore. However, this is different for the case C, where we indeed find localization. So to summarize this plot, we now have the case that for delta J 0 smaller than 0.58, both regimes coexist, and for larger ones, there's localization for all times. We could then also we then also looked for certain particles just at the slope of this curve here at t equals 0. So to say, what we did was we fitted these curves here by hyperbola with known asymptotes, and then by this fitting we could obtain here the slopes at t equals 0, and we, as I just said, we looked at n equals 13, and we also could find from this the indication that there is this transition happening at 0.58. Here we could determine was also the Thouless time. So to say, we fitted in this case, we again took our curve here in the regime of small values of t, and we now wanted to find out the Thouless time, or determine it. So to say, Thouless time is just the time when the spectral form factor, or the difference of the spectral form factor of the system itself and the RMT form factor is much smaller than the RMT form factor. And by fitting these curves by this function given here, we then obtain that it depends also logarithmically on n. So this brings me now also to the end of the second part of my talk. I have now shown you the characterization of the properties of the Kicked-Ising spin chain for S equal 1/2. And in the regime where self-duality is not anymore present, we have done perturbation theory on the one hand, so to say, in both regimes, so in the vicinity of self-duality and in the vicinity of J equals 0. And in the intermediate regime, we were able to study the system behavior and find a convenient quantity to analyze localization by the ratio of spectral form factors. So this now brings me to the full conclusions of my talk. I have first established or explained to you how we actually came to the duality relation and why it was interesting for us and what motivated us to study it. And then I explained to you our two main applications of it, so to say, to get the classical orbits from the quantum spectrum on the one hand for a system with S greater than 1/2, and then on the other hand to also look at the duality relation and to see how it allows to characterize, in the case of spin 1/2, the transition from ergodic to localized behavior. So, and with that, if you are interested, you can have a look at our references concerning this work, and I now want to close and thank you for your attention.
Thank you, Daniel. Thank you for brilliant talk. So now the stage is open for the question. So we have some time to discuss, and if somebody has any question, please feel free to ask to Daniel.
Hello, maybe I have a short question. Do you hear me?
Yes, I can, but Daniel, can you hear?
Yes.
Great.
Yeah, so my question would be, have you tried also to lower have you tried to lower the disorder value? So probably you took the maximal disorder, but if you would, let's say, try to study the spectral form factor in the clean limit, maybe you would need to unfold into the symmetry sector. Have you looked into this?
Well, we have also lowered the disorder. We didn't look at a clean limit, and we saw that it was not so relevant how large the disorder was. So as long as it was already, there was some disorder, it already went quite well, but we didn't look at a clean limit.
Because if I would expect that like the ratio of J effective where you see the transition would change if you would lower the amount of disorder. So you saw this J 0.58, and if you would have lower disorder, probably this would change or not. That's my question.
Well, actually, I wouldn't be so sure how universal the result, if you would not just end up with a largely fluctuating quantity, if you would look at the spectral form factor without disorder. Or do
Maybe you could also
would you
average
expect that
average over time or something like that.
that might be possible? That's a good suggestion, yes, but we have not looked at that. But thank you very much for the suggestion.
Okay, so is there any other question? Okay, Daniel. So,
yes,
sorry.
Ranjan, thanks, Daniel. Nice talk. I have a sort of a general question, maybe. Since you are especially interested in the short time, at least you were interested in the short time dynamics, is there an analog of the Ehrenfest time scale? Can you see something like that? I mean, I know that in scrambling, you can define a scrambling time via an OTOC, but is there some other way of looking at finding out an Ehrenfest time scale in this problem, in these kind of many body problems? I have a semi-classic.
Yes, in the sense, I'm now not so sure what you mean by an Ehrenfest time, so to say. Let me say it that way. I mean, an Ehrenfest time is for me a time after that random matrix theory occurs or applies, so to say.
Yeah, well, maybe that's what you would call a Thouless time, but
yes, then it's the Thouless time, which we just studied. But that's probably not what you meant, or?
Not really, because you have a semi-classical limit in your. So I mean, in the usual Ehrenfest time, you would say classical quantum correspondence breaks at that time. And since you have a semi-classical limit, I'm wondering whether in your many body systems you can infer such a time scale. Because I would imagine that that's also a short time scale.
That's true that you could do, but so do you think that there would be a difference between this time scale and an Ehrenfest? Sorry, a Thouless time. So as I read, in many cases, the Thouless time and the Ehrenfest time is the same, used as something which has the same meaning.
Yeah.
So, but you are right. I mean, if we would study this system for a larger spin quantum number, then we could do some semi-classics for it. That's true, but I think this is also something which was already done.
Okay.
I just remember this work of John Chalker.
Yeah.
And looked at similar systems for larger spin quantum number.
And
so my interest was more to look at a non-classical system.
Your interest was not to look at a non-classical. or was to look at a non-classical?
Was to look at a long classical
Yeah.
system.
Okay.
Yes.
Yeah.
But you're right. I mean, certainly the Ehrenfest time, but the Ehrenfest time would probably be best to determine, if I would use your language, in some encounter context, or that you would say you have then again a pairing of periodic orbits, and there you could then indicate Ehrenfest times. Huh?
Okay. And may I just ask one more question about mixed dynamics? I mean, the mixed phase space dynamics of lower dimensional systems in the many-body context, did you see systems, so near integrable maybe, or where you have a statistics which is intermediate? Because you also have all these scarring in many body systems and that kind of scenario, where actually the scarring is not due to unstable periodic orbits. So do you see signatures of mixed systems in the thermodynamic limit?
So now I can, of course, answer this question for the two parts, I think. So to say, if we look at this back at our semi-classical connection, oh, sorry, now seems here we are. Yes. So to say, for this system, for the classical dynamics, we have mixed dynamics naturally. I mean, I didn't explain this into great detail, but we have, for our system, we are considering all kind of periodic orbits. So we have bifurcating periodic orbits, we have also unstable periodic orbits, we have stable periodic orbits. They are actually indicated here. I went very quickly over this by these different colors. And also we have this collective kind of motions, which are just indicated here by green lines.
Yeah.
So in that case, we see really all kind of dynamics, which are then occurring in a mixed system.
Okay. Okay. Thanks.
Okay, so do we have
You're very welcome.
Any other question from the audience? Okay, so if not, then let's again thanks Daniel, and let me thank Sohail and Daniel both again for beautiful talks. So I guess so it's in Indian time it's 8:10. So maybe we will meet again in 20 minutes. So Arvinda, you want to say anything?
Yeah, so we will meet. There will be 20 minutes break, and we will meet at